You think black holes are empty voids in space, don't you? Massive gravity wells that swallow everything. Light, matter, entire stars all falling in, never coming back out again. Dark, silent, and dead. Everyone thinks this way. Einstein thought this way too. For decades, every physicist thought this way. Wrong. Black holes aren't dark. They're not empty. They're burning. They're glowing. They're radiating energy like hot coals. And when Stephen Hawking proved this in 1974, he shattered physics. He destroyed everything we thought we knew about black holes, quantum mechanics, and the nature of reality itself. You heard that right, that's exactly what happened. This isn't just some ordinary theoretical curiosity. This is one of the most profound discoveries in the history of science. And almost no one understands it. Let me show you right now what Hawking discovered. And why it's so deeply, profoundly strange. Let's start with what you already know. A black hole forms when a massive star collapses. All that mass rushes down into an infinitely small point. The gravity becomes so strong that nothing can escape. Not matter, not light, nothing. There's a boundary around the black hole called the event horizon. If you cross that boundary, you're done. You're falling toward the center forever. You can't turn back, and you can't escape. You can't do anything, because the gravity is too strong. And here's something most people aren't even aware of. The event horizon isn't a physical surface. It's not a wall. It's not made of anything. It's just a mathematical boundary. There's no point of return. If you were falling toward a black hole, and you crossed the event horizon, you wouldn't feel anything different. No bump, no barrier neither exists. No sensation of crossing through anything. You just keep falling. But from that moment on, every direction you could possibly move would point toward the center. Forward is toward the center. Backward is toward the center. Left, right, up, down. All directions lead inward. Space itself has been so warped that unfortunately, there is no path leading out. Einstein's theory of general relativity tells us exactly this. Space and time curve around mass. The more curvature. A black hole has so much mass packed into such a small space that the curvature becomes infinite. Space folds in on itself. Time stops at the horizon. Everything falls in. Nothing comes out. Nothing can come out. For 50 years after Einstein published general relativity, physicists believed this was the whole story. Black holes are like one-way streets. They're perfect traps. They only grow. And they only swallow. They never give anything back. A black hole was thought to be the most permanent thing in the universe. Once formed, it lasts forever. It grows bigger and bigger as it swallows more matter, but it never shrinks in any way. It never evaporates and never dies. Then Hawking came along, and he asked this very simple question. What happens if you apply quantum mechanics near a black hole? Not inside the horizon. That's too complicated. Just outside. Right at the edge. And when he did the calculation, he found something impossible. Black holes were glowing. Now, you might think, okay, that's interesting, but so what? Things glow. Hot things emit radiation. There's no problem with that, but you're missing the point. Black holes aren't supposed to emit anything. That's what makes them black. Nothing can escape. Not matter, not light, nothing. If a black hole is glowing, something is escaping. And that means it's violating the most fundamental rule of black holes. Here's what Hawking realized. Empty space isn't empty. This is quantum mechanics. At the smallest scales, Space is boiling with activity. Particle pairs constantly pop into existence. An electron and a positron, a quark and an antiquark. They appear out of nothing. They exist for a millionth of a second. Then they collide and annihilate back into nothing. These are called virtual particles. In the normal sense, of course they're not real. You can't catch one. You can't measure one directly. They exist for such a short time that they don't even violate conservation of energy. They borrow energy from the vacuum, but they pay it back instantly. You can think of it like quantum bookkeeping. As long as the books balance fast enough, the universe allows it. Now, you might wonder, if we can't see them, how do we know they exist? That's a good question. Because we can measure their effects. Virtual particles affect how real particles behave. They change the energy levels of electrons in atoms. And through this, they create tiny forces between metal plates in a vacuum. These effects have been measured with incredible precision. Virtual particles are as real as anything in quantum mechanics can be. This happens everywhere. It can happen right now, in this room, in empty space. Particle pairs are constantly appearing and disappearing. Trillions of them disappearing. Every second. You don't notice because they vanish so fast, but they're there. Quantum mechanics guarantees it. Now, this is where things start to get even more interesting. What happens if a particle pair appears right at the event horizon of a black hole? One particle forms just outside the horizon. The other forms just inside. Normally, they would annihilate, right? But we know the one inside the horizon can't come back out. It's trapped. It falls toward the center. It's gone forever. So what happens to the other particle, the one outside? It has no partner to annihilate with. It becomes real. It escapes. It flies off into space as real radiation. This is Hawking radiation. But here's the thing that should blow your mind. Where did that escaping particle get its energy from? It can't come from nothing. Energy is always conserved. The energy had to come from somewhere. And the only place it could come from is the black hole itself. The particle that fell in had negative energy from the black hole's perspective. It reduced the black hole's mass, and the escaping particle carried positive energy. Therefore, as a result, the black hole lost mass and shrank. Black holes evaporate. Slowly. Very, very slowly. But they evaporate. They're not eternal. They're not permanent. They're temporary. Given enough time, every black hole will radiate away all its mass and completely disappear. For a black hole the mass of the Sun, this takes approximately 10 to the 67 years. That's a 1 followed by 67 zeros. Incomprehensibly long. The universe is only 10 to the 10 years old. So we're not going to see a solar mass black hole evaporate anytime soon. But smaller black holes evaporate faster. A black hole the mass of a mountain would evaporate in about a second. And with the tremendous explosion of energy. And here's something fascinating. As a black hole loses mass, it gets hotter. You'd think it would cool down as it shrinks. But the opposite happens. Smaller black holes have higher temperatures. They radiate faster. And the faster they radiate, the faster they lose mass. This makes them smaller and as a result, hotter. It's a runaway process. In the final moments of a black hole's life, it becomes incredibly hot, radiates furiously, loses mass at an exponential rate. Finally, it explodes in a burst of energy and completely disappears. Think about what this means. Black holes have temperature. They glow. They radiate heat, just like everything else. A black hole the mass of the Sun has a temperature of about 60 nanokelvin. That's 60 billionths of a degree above absolute zero. Incredibly cold. Much colder than the cosmic microwave background radiation filling space. So right now, black holes are actually absorbing more energy than they radiate. They're growing. But eventually, the universe will cool down. And black holes will start losing mass faster than they gain it, and they'll evaporate. But here's the problem. The real problem. The problem that has haunted physics for 50 years. Information. When something falls into a black hole, it carries information. The positions of atoms, the spins of electrons, the quantum states of particles, all this information crosses the event horizon and disappears. Now, if the black hole lasts forever, that's fine. The information is gone, but it's still there, trapped inside. But if the black hole evaporates, what happens to the information? Does it come back out in the Hawking radiation, or is it destroyed? According to quantum mechanics, information cannot be destroyed, ever. This is a fundamental principle. You can scramble information, you can hide it, but you cannot destroy it in any way. In principle, it must always be recoverable. Even if you burn a book, the information isn't destroyed, right? It's in the ash. It's in the light. It's in the heat. Scrambled beyond recognition, but not destroyed. But Hawking radiation is thermal. It's random. It's heat. There's no information in it. The black hole is like a furnace. You throw in an encyclopedia. You get heat out. The information is gone. Destroyed. This is the black hole information paradox. Hawking's own discovery created it, and for decades, no one could solve it. This suggested that either general relativity was wrong or quantum mechanics was wrong. One of our two most fundamental theories had to break down. But which one? Hawking himself believed the information was destroyed. He said quantum mechanics had to be modified. Not everyone agreed. Other physicists, including Leonard Susskind, argued that information must be preserved. That somehow, the information comes back out encoded in the Hawking radiation in a way we don't yet understand. The debate got heated. Hawking and Susskind argued for years. Public lectures, debates, papers. Both sides were convinced they were right. It became one of the most famous disputes in modern physics. Hawking even made a bet. He bet that information was destroyed, that quantum mechanics had to give way. In 2004, Hawking conceded. He admitted he was wrong. He accepted that information is preserved. A baseball encyclopedia. He signed it and gave it to the winner. But how? No one knows for sure. The leading idea is that information is stored on the event horizon itself, like a hologram. Every bit of information about what fell in is encoded on the surface. And when the black hole evaporates, that information is released back into space in an incredibly scrambled form. Isn't that interesting? This is called the holographic principle. And it suggests something profound. That the three-dimensional interior of the black hole can be completely described by information on the two-dimensional surface. That in some sense, the volume is an illusion. Only the surface is real. Some physicists think this applies to the entire universe, that we're living in a hologram. That all the information describing our three-dimensional world is actually encoded on a two-dimensional surface at the edge of the universe. That's speculative. But it comes directly from trying to understand Hawking radiation. Here's another thing that should completely change how you think about reality. Hawking radiation means that quantum mechanics applies everywhere, even to the largest, most massive objects in the universe. Before Hawking, people thought quantum mechanics was just for small things, atoms, photons, electrons, At large scales, classical physics takes over, but Hawking showed that was wrong. Black holes are huge. They have the mass of millions or billions of suns. And yet quantum mechanics affects them. It makes them radiate. It makes them evaporate. There's no escape from quantum weirdness whatsoever. No matter how big something is, quantum mechanics still applies. Of course, this has huge implications. It means we need a theory that combines quantum mechanics and gravity, a theory of quantum gravity. String theory is one attempt, loop quantum gravity is another. We don't have a complete theory yet, but Hawking radiation proves we need one. And here's why this matters so much. General relativity and quantum mechanics are our two most successful theories. They work incredibly well in their own domains. General relativity describes gravity, black holes, the expansion of the universe. Quantum mechanics describes atoms, particles, forces, but they use completely different mathematical languages. They make different assumptions about how reality works. And when you try to combine them, you get nonsense. Infinities, contradictions, and the equations break down. But at the event horizon of a black hole, both theories apply. You can't ignore gravity. The curvature is too extreme. And you can't ignore quantum mechanics. The effects are too important. Hawking radiation exists precisely because both theories are operating at once. A window into quantum gravity. The only window we have. Now, let me tell you the most mind-bending part. The thing that should keep you up at night. Virtual particles. Remember them? Particle pairs that pop into existence and disappear. We said they're not real. Just a mathematical convenience, a way of talking about quantum fluctuations. But Hawking radiation forces one of those virtual particles to become real. Think about that. Something that shouldn't exist, something that's supposed to disappear immediately, gets ripped apart by the gravity of a black hole, and becomes actual, measurable, real radiation. The vacuum, empty space itself, is not nothing. It's a seething foam of quantum activity, and under the right conditions, that activity becomes real. The universe is stranger than you think. Empty space is full, virtual is real, nothing is something. And black holes, the darkest objects in the universe, glow. This discovery, Stephen Hawking's insight, connects general relativity, quantum mechanics, thermodynamics, and information theory. It touches every corner of physics. It reveals deep connections between things that seem completely unrelated. And we're still trying to understand it. 50 years later, we know black holes radiate. We've done the math. We trust the calculation. But we haven't seen it. We probably never will. The radiation is too faint. The black holes are too far away. We can't detect it. But we believe it's real because the math is too beautiful, elegant, and right. That's how physics works sometimes. You calculate something that seems impossible. You check the math 100 times, and if it keeps coming out the same way, you accept it, even if you can't see it. Even if it contradicts everything you thought you knew. Hawking changed how we think about black holes. He changed how we think about quantum mechanics. He changed how we think about the universe, all with one calculation. All by asking, what happens if I apply quantum mechanics near an event horizon? And the answer broke physics, in the best possible way. It showed us that black holes aren't dead. They're alive, dynamic. They interact with the universe. They have temperature. They have entropy. They evolve. They die. And we realize nothing is permanent. Not even black holes. The universe is more subtle, more complex, more interconnected than we imagined. And we're still figuring it out. So what is Hawking radiation really? It's proof that quantum mechanics and gravity interact. It's proof that information matters. It's proof that the vacuum is not empty. It's proof that black holes are not simple. But more fundamentally, Hawking radiation is proof that we can understand nature. Proof that we can take two theories, quantum mechanics and general relativity, theories that seem incompatible, and find the places where they overlap, the places where both have something to say. And when we listen carefully, we discover something new, something no one exactly expected. Great physics does this. It doesn't just answer questions. It shows you that you were asking the wrong questions. Before Hawking, we asked, how big can black holes get? Hawking asked that simple question, can they shrink? And that simple question changed everything. Next time you look up at the night sky, remember this. Somewhere out there, there's a black hole, and it's glowing. Faintly, invisibly, radiating energy stolen from the quantum vacuum. Slowly evaporating, slowly dying. And that glow, that impossible radiation, is proof that the universe is stranger than we thought. That empty space is not empty. That nothing is something. That virtual particles are real. And that even the darkest objects in the universe cannot escape from quantum mechanics. That's what Hawking discovered. Not just that black holes glow, but that reality itself is deeper, stranger, and more beautiful than anyone imagined. And we're still trying to figure out what it means. That's the answer. And it changes everything.